Hello everybody, in this lesson we are going to see how to determine the ideal theoretical price for options. Okay, every student of economics knows that there is the Black-Scholes formula to determine the price of an option. It's here, starts from differential equations and blah blah blah, solve them, blah blah blah, find a solution, not solve them. And here it is the formula. Okay. However, I tell you, many practitioners calculate the price using the Black-Scholes formula and then don't trust it too much and do numerical simulations to determine if the price at least is within a reasonable range, if the price determined by the formula is within a reasonable range. That is what we are going to do today. We will not use Python to calculate the Black-Scholes formula. It's too easy, honestly too easy, even though there is a statistical distribution inside, but it's too easy. We will instead do numerical simulations to try to forecast the future prices and therefore have an idea of what the price of the option could be. I take for granted, obviously, that you have a very well knowledge of what is an option, don't you? I will be personally offended if you arrive at this point of the course and still don't have any idea what is an option. Okay. We will talk about European options, so options which can be exercised only at the end and not during their life. So we have call and put options, and then we'll have a strike price. Okay, so we start here, we set the time. This is the amount of trading days. Pay attention, not the amount of days, the amount of trading days before expiration, so before it can be exercised. Okay, this is the strike price. I take, for example, Procter & Gamble. Okay, before setting the strike, okay, let's take 155. So we suppose let's say, call option 155, which expires in 50 days on Procter & Gamble, so 2 months. Okay, now let's try to estimate the future price of Procter & Gamble. We will not make one estimation, obviously. We'll use a Monte Carlo technique and we will make several estimations, so we'll have a distribution of prices, and therefore we could have an average price for the option and then a distribution of how the returns of the option could be. Okay, let's start. We import all the usual stuff and take also the prices on Procter & Gamble. Okay, let's take a look at them. Oops. Okay, 1056. Strike 1055. Okay, I prepared the video yesterday, it was 1051. Okay, let's change it. 1060. Okay, so okay, something which you cannot do in real life. Okay, we determine the start price of our simulation, which is this one, 156. So it's prices of -1. It doesn't work, I think. Yeah, does it work? Ah, yes, it was. Also, you could also type .iloc. Okay, very well. And now let's determine the logarithmic returns. I take for granted that you have already attended the Monte Carlo simulation lecture. MP log of prices divided by prices dot shift 1. Okay. Okay, let's take a look at it. B. Always take a look at it, you never know. Okay, yes. And now the drift, which was log ret dot mean minus log ret dot var divided by 2. Okay, and let's also take a look at it. Okay, this is the drift, it's positive, so it's going to go up. Okay. Unlike what we did last time, we're not really interested in what happens within these 50 days. We would be if this were an American option in which could be exercised also during its life. but it's an European option, so we are not really interested in what happens during these 50 days, so we don't care in storing all what happens during these 50 days. We care about, so we don't create a data frame which stores everything what happens. We care only about what happens at the end. So we set up a forecasted price, which will be a series, which for the moment it's identical to start price. So it's a series with how many simulations do we want to do? Well, now we will not just plot a graph. We need a ton of simulation because we want to be very sure. I mean, we are going to invest our money. So PD series, so create a series. Okay, we want to create a series with 100,000, I'm not joking, 100,000 elements, okay, which all will be equal to start price. Okay, I don't think it will work if you do something like this. Let's see. Oh, perhaps it works. Tell me that it works. No, okay, obviously. Okay, because it doesn't know that it's under 1,000. I'm perhaps if you do like this. No, obviously no. Okay. What is it? Okay, so how do I do it? I use the following trick. Look. This NumPy once create a matrix or an array depending on what you type here in the middle. Okay, in this case I typed only one number, so it's an array of 100,000 ones. The function is called ones. It's the same as the NumPy zeros, the NumPy ones. I multiply everything by start price, so now I have. Okay, and now you understand why I don't keep all the 50 days, because I have already 100,000 simulations going on. If I have to keep all the 50 days, I will have 5 million numbers to keep trace of. So I will just keep these things. Okay, that's it. Let's estimate, calculate the volatility, which will be log ret std, as usual, by, okay, uniform distribution, uniform, okay, between -1 and +1 with 100, no, 50 times 100,000. Okay, so this generates a matrix with 50 because we need one value for each step. We cannot have just a vector with 100,000 values, because otherwise every day will be identical to the previous one, which is something unrealistic. So we have a matrix with 50 days and 100,000 simulations. Okay, and exp daily returns equal numpy exp of volatility drift plus volatility. Okay, exp the returns up. Okay, so we have what's the size here? 50 rows and 100,000 columns. Let me np.shape will tell you the shape of this object here. 50, 100,000. Okay. Okay, so these are the modification with respect to the previous day. Okay, now we go on with the usual simulation for I in range 1, 51. So this will produce numbers from 1 to 50. Okay, Python has this feature that it never arrives up to the last one. Okay, forecasted price is equal to the forecasted price. In the original Monte Carlo simulation, we had forecasted price of I equal to forecasted price of I minus 1, because we wanted to keep all the steps. Here I don't want to keep all the steps because it's too much information. Okay, so I simply go ahead, overwrite the old data. Overwrite the old data. Okay. The only thing which changes every time is this one. I minus 1, because this one starts from 0. This 0, here instead the range starts from 1. Okay. Let's see. Forecasted price not defined. Let's copy it because I must stop using long names. Okay. What's the problem? Operands could not be broadcast together with shapes. Okay, forecasted price has 100,000. X daily returns of I minus 1. It's 1 million. One of them is 1 million. There is a mistake somewhere. Here, it's not 1 million, it's 100,000 are enough. Okay, 100,000 are enough. Okay, so this is our 100,000 estimation of the price. You can see sometimes it's very high with respect to our strike price, which is 160. Other times it's lower. Okay, so we estimate the gain. The gain is, I remind you that in case of a call option, the gain is the forecasted price minus the strike price. Okay. In case of a put, it's vice versa, because in a put you wish to be lower than the strike price. Okay, this is the gain. However, since it's an option and not a future, you're not forced to exercise it. If forecasted price minus strike it's negative, you will simply not exercise it and your gain will be exactly 0. Okay, so we have to set, so you can see some of the gains are negative, but for an option, for a future it happens that when you arrive at the exercise date it's negative, so you have to pay, but for an option it's not an option. So we have to set all these things to 0. The trick is the following. I say gain of, and now here I should specify 0, 2, 3, 99997, okay, and I can specify them in this way. So the gain of all those which are smaller than 0 will be set equal to 0. And you can see they have been set equal to 0. So now this is our situation. In several cases, you will have a 0 gain, all the cases in which you are below the strike price. In other cases, you will have a non-zero gain. Okay, let's start with the statistics on gain. First of all, the average gain is 2.6, and this is the correct price for the option. So the price for this option, not considering the fact that time, there is 50 days of investment in the middle, it's 2.6. So on average, you're going to gain 2.6, so you should be willing to spend 2.6. A little less, let's say, because there's time which passes. Okay, but I am curious about the distribution, because perhaps it's 2.6 because in one possibility out of 100,000 I gain 3 millions, and in all the other possibilities I gain 0. So how to get an idea of the distribution? We have the wonderful method value counts. I've never understood why it's value counts and not values count, but okay, value count simply counts how many values. So you see that you have 53,989 zeros. So in 54% of the cases, you will end up with no gain. For about half of the times, you will end up with no gain. Okay, and let's plot the distribution. The histogram is the best thing here. Plot kind equal hist. For the moment, let's try like this. Okay, no, I would like to have more beans. Beans equal 100. I have 100,000, so I could use 100 beans. Okay. Unfortunately now, this, as we have seen before, takes 50% of the cases, and the other one are squeezed. So how can I zoom here? It would be interesting to see this distribution. How can I zoom here? Well, if you wish to zoom, just ylim equal, and you specify the lower, which is 0, and the upper, which is perhaps 300. Let's see. No, 300, something more, 900. No, even more, 2000. Okay, 2000. So this one we know goes up to 50,000, so it's 50%. And then you can see the distribution of your gain. There are some cases in which you will gain 20%. These are the cases in which you will gain, 20 euros, in which you gain 15 euros. Or better, you will gain 20 euros if the price is 0. So these are cases in which the ideal price should be 20 euros, the ideal price should be 15, 10, 5. Okay, so I bet you can bet around 5. Okay, so very well. Perhaps with 50 beans it can be even better. In this case you have to raise the limit. Okay, 50 beans, it can be even better. Okay. This was done using a simulation, but I ask myself, why should we use simulated data, so not true data? Because you have made the hypothesis that first of all there is a drift with a constant minus var divided by 2, which is not true even statistically. Second, you have supposed that the volatility it's uniform. Who knows? Okay, so I say instead of simulating the log ret, we could instead take the log ret value from the previous data. So I have here, how many? Where are they? Here, 3000 previous prices and consequently 3000 previous log ret. Okay, I could every time I go on take a random value from this 3000 log ret. So in this way I take the log ret from the real distribution, always of past data, but the real distribution. So we see this one is very common in statistics, but in particular in computer science, and computer scientists love it a lot. I've seen it more rarely in economics. Okay, so instead of using drift plus volatility, I will use that log ret taken from the past data. So since I take it randomly, I should decide which value to take. So I should build a random index np.random.uniform. Sorry, not uniform, but let's start with uniform. Uniform from 0 up to the len of log ret. So this will extract a number from 0 up to the len of log ret, okay, and we'll create 100,000. For the moment, only 100,000. What's the problem? The problem is that it takes fractional numbers. Okay, I could just simply round it and I get integer numbers, but I have a better function, randint. Okay, randint is same as uniform, but takes integer number. This means, for example, that the first day we will use a return of day 2052. The second day we'll use the return of 3300, day 3361. Third day the return of it can be repeated, so for sure there will be some log ret which will be repeated, other will not be taken, so but it's taken randomly. So I have the pool of the log ret, I pick randomly some log ret. And these are the historical ones. Okay, so random log ret equal log ret of random index. Okay, random. So you will just, I'm doing it slowly. So you can see, these are log ret. There is, however, a little problem in doing something like this. Look at the dates. Unfortunately, Python is so smart that remembers the original date. So this one was the log ret of the 27th of February 2017. This was the log ret of the 14th of December 2021. So I have to kill this information here, otherwise it will create problems later on. So if you don't mind, I will do also log. I will put also here numpy array. So I convert this series. I do the vice versa of what I usually do. Usually I have a series and a numpy array and I convert into a series. This time I have a series, I convert into an array. So Python will, you can see Python now has forgotten the fact that these are bound to a specific date. Otherwise, when you will mix it with other things, Python will become crazy. Okay, pay attention to tilted dates. Okay. Okay, now I have to apply also the exponential, because I remind you that in the original formula, where is it? Where is it? Where is it? Here. No, here there is the exponential. So np.exp. Okay, at this point it's not the logaret, but we call it the logaret anyway. Okay, and this is what happens. So the first one will be a drop, then a slight increase, a big drop, etc., etc. These are all historical numbers, so they really happen in the past. Not in this order, obviously. Okay. So now, let's put everything together. Okay, I have, as usual, let's go. FP is forecasted price. I am tired of writing it. FP equal pd.series of np ones of 100,000 multiplied by start price. As usual, this is the usual thing. Okay, now for I in range 1,51, yes. Op. And here fp equal. Now, first of all, I have to create this stuff here. Oh, but I have it. Yes, first of all I have to create this stuff here. So at every step, I don't store all the random numbers. At every step, I recreate 100,000 random number. At every step, I create the random logaret whatever, and np equal np, no, fp, no, fp equal fp forecasted price by this thing here, which honestly it's not, I call it random logaret. Let me call it instead exponential of random logaret. Exponential of random, okay, exponential of random logaret. Okay, I think it's done. Okay, let's see, because I have some doubts. Okay, why a none here? Let me redo it. Okay, no none. Very strange that there is a none. Perhaps... oh, seems correct, everything. Okay. Okay. Let's calculate. I'm sure, is it a good idea according to you to convert into a series now or keep it as an array? Let's keep it as an array. Okay, let's calculate the gain. Gain equal forecasted price minus strike. Okay, in case of, as usual, gain smaller than 0 will be set equal to 0. Let's take a look at this gain. Yes, a lot of zeros. And now gain dot mean 5. So why with this simulation is 5 and before here it was 2? Well, the reason is because in the Monte Carlo simulation we have these horrible things of the drift. It's here. Can you see the drift, which should be simply the logaret mean? We have added a minus logaret var divided by 2 to be conservative, which is clearly killing the stock. It's killing the gain. It's going down. Okay, if this could make sense if you are forecasting the price of a stock because you want to buy it, it could make sense, but not too much if you are forecasting the price of a call option. But for sure, it doesn't make sense if you want to forecast the price of a put option, because in order to stay on the safe side for a put option, you will have to put minus. So while forecasting options, I would not put this part here, especially because if you put, you can see you arrive to an ideal price which is much lower than the ideal price to which we arrived using the real data. Okay, anyway, you just change it above. Let's see, 5.11, if I change it above, will I get such a big difference? I'm curious now. So I have to change it here, so I remove it. Okay, I start from here. Ta, 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 ta. 2.8, always the same. So the drift didn't have any impact. Okay, let's redo it. Okay, the 2.8, yes. The drift didn't have such a big impact. So now, so probably also the effect is that the fact that here the uniform distribution is very optimistic. In real life, they fluctuates much more. And if it fluctuates, it means that it's a big advantage if you have a call option and it fluctuates. Because if a call option fluctuates, okay, probably most of the time you will gain 0. But most of the time you will gain a lot. Okay. So since it's bound here to 0, so you can never lose money. If when you are here, it's a very advantage if it fluctuates a lot, because when it fluctuates positively, you gain a lot. When you fluctuate negative, okay, you go to 0, which is the same when you fluctuate a little. So probably the real data fluctuates much more than a uniform -1 +1. Okay, so same thing as before. It's values count. No, value counts, as I told you. Value counts. Okay. Okay, 51 times it goes below. Let's see the histogram. Okay, histogram is not so different. 3.5% here, and here the histogram 3.5%. And here we arrive with a tail. The tail is visible at 20, almost invisible at 25. And here, oh, here seems slightly lower the tail. The tail seems to go down stronger. Okay. There is a little mistake here. Okay, the lesson is over. It's over. Yes. Bye bye.